my phone just like locked out of nowhere and the phone stopped. But yeah, coming back to this. You don't do this with equality, you do with an if-then statement. So actually, here's how we do it. So B T C implies, this is where I was wrong. And then you do for all A implies. And yeah, I'm just like, I want to spend a lot of time thinking about like if you can almost like measure the complexity of a given formula, like how many different symbols are in it, how much nesting is there, how complicated is it, how long is it, almost like a combinatorial exploration of formula. Anyway, BTC implies for all A or B implies ARC, just to try to stimulate the kinds of questions that I'm thinking about. Like, what if we just pulled out components of this and just imagine them as axioms? So, like, let's just say we have a theory with the formula, like, well, if we just started with, like, ARC or something. Okay, this can only be a formula if A and C are constants, first of all. So then it can be valid. If they're variables, I do not believe that counts as a formula. They have to be quantified. So then, one second. If they're variables, then we can use a quantifier. So first I'll try for all, and then I'll do there exists. For all A and C, ARC. Now that is just saying, if A and C are variables, they need to be quantified over. And this is just saying that this relation is, I don't know what you would call it. It's like left total and it's right total. It's just this like bland relation which just happens to relate everything to everything. But the cool thing is that means that it's actually a product on the domain, I believe. Okay, let's go on. Consider some other options. Here's more interesting ones. For all A, there exists C such that ARC. Now that is actually the definition of left total for a function. That's really cool. And then you can have there exists, and if you flip that around, wait a second. There exists an A such that for all C, there exists an A. Okay, yeah, that's also interesting. I was wondering if I switch A and C, for all C there exists an A, so that would mean that would just mean it's right total, which is interesting to think about. But then I was wondering if that would be the same as if I switched the quantifiers, and I think the answer is no. Like, there exists an A. Yeah, it's interesting because I never even thought about if like universal and existential quantification commutes. I've never even thought of that before, and I feel like I would have thought the answer is yes. But then when I look at this example, I think the answer is no. So let's put this one in. There exists an A. Actually, there exists an A and a C, such that A or C. And that says something very boring, which is like this relation has at least one element. One second. How do I make it smaller? There we go. Well, no. Okay. The subset relation relates to sets is defined as that every element in one set is in the other. And then here we start to explore some relations. Oh yeah, and I was wrong about writing that with equality. Then we have a better version with implication. And that makes me think, in a weird way, there's like some kind of connection between implication and equality, I feel like. I'd like to see that, like, some kind of way of showing what way they're analogous to each other, because I feel like in deductive systems, like, implication is the most important relation. Like, in other situations, equality is like, there are a bunch of logical connections and relations, but equality is like the most important one. It has like a special status. And I just feel like we could say the same thing for implication in certain contexts. And the thing is that with modus ponens, so the thing is, like, in some situations, equality is used for a substitution rule. But in some situations, implication plus the rule known as modus ponens also enables a kind of substitution. So, like, I think there's some kind of interesting parallels there. Okay, now we have some axioms. One second. Okay, the first one is nothing. The second one is the definition of a subset, which I was going to explore more abstractly. The third is just saying that there's happens to be a certain relation on two constant elements. The fourth is saying that the relation is like maximal, I guess you could say. It holds for all possible pairs. And as I said, it'd be cool to explore further. Like, it'd be weird if this was like an alternative definition of the product, or if we could show algebraically that it like reduces to the product with a little bit of symbolic manipulation or something. Or if it would be interesting to think of products as like maximal relations, like turning it around or something. I don't know. Here we have, for all A, there exists a C. That's left total. If we switch A and C, we get right total. And there's another idea, is like, it's not like commutative. But if you switch it, it's like there is definitely a corresponding idea. And that's like the idea of duality in category theory. Again, need to think about it more, but it's just interesting that there's some things you can't switch at all. It just completely changes the meaning. There's some things you can switch and it doesn't change the meaning at all because it's symmetric or commutative. And then there's things where, like, if you switch them, it's not the same, but it's like a corresponding mirror image or something. Like, there's a kind of symmetry in it, I think. Anyway, for all A, there exists a C such that A or C. And then I have this one that's like kind of similar to the total one, like for all. This is like very minimal. Like, instead of saying that it's defined on all relations, we're saying that it's defined on at least one relation. Or at least one, the relation has at least one element. And basically, that's enough for now. I'm going to go back to this and try to think about this more. Okay. And I guess we have to say for all here also. And again, there's like so many small details that I need to learn and get way better at, which is just kind of what I'm realizing while I'm doing this. So for all A and C, for all B and C, BTC implies that for all A, ARB, and like I'm now asking myself the question, can I somehow factor out this for all? Like, it would be fascinating to create some algebraic rules, just like dealing with with quadratic equations, like just simple rules for how you can bring quantifiers like in and out of, implications, formulae, and stuff like that. No, but I think this is wrong, actually. I'm actually very confused because if I don't quantify immediately over BTC, then I have unbound variables, and I don't know if that's allowed. I think I've written it correctly. For all B and C, it's like saying, regardless of what B and C are, if you ever write something T something, then what that actually means is that for all A, ARB implies A or C. Oh, man. It's like, there's like so many questions I want to ask about this. But I might just leave it behind for now. I'll just think for a second. Like, I'm wondering if we could break it up and make it seem more like a function, like in a more functional way. Like, if you ever see for all BC, like, does that almost imply you just referred to a domain of a function? Because it's assumed that a function is going to be defined on all, elements on its domain or something. So, like, I'm just thinking, what if we wrote like more like a function like t, b, c, equals it's like I'm converting like universal quantification into function. So I'm wondering if I should like, it's kind of like lambda calculus or something. You have a function that returns a function. I'm wondering if I could put that in here, like r of a man, this is so weird. I'm like converting implication into equality, but like, but maybe this could work. Equals r a, like I need some time to try to formalize this, but it's a cool intuition. It's like there's some way we can convert these kinds of statements into these kinds, if this could work in some way with some modification. I'm going to leave this question hanging. I think this is interesting stuff. So yeah, I feel like this could all be like its own sub-exploration, just all these questions I have. I might even need to take a break now, I'm not sure. So just to verbally summarize, here's what happened. I am going to take a break now, but this is productive. I was trying to think more precisely about like restriction, the condition that there has to be like a restriction mapping or something like that, restriction condition, restriction function, I can't remember what it's called. And then I was just thinking about how like if behavior types or behavior sets are what I call downward closed, then to what extent can that just be understood as the power set? And then I was just trying to define power sets in formal logic, and then I was exploring like what the meaning of that axiom is just purely syntactically and forgetting the interpretation in terms of sets. So I think this is a cool exploration, and yeah, looking forward to continuing.